Okay, so let's continue on trap ion. So on Monday's video, have you watched it already? Okay, it's 1 qubit. You find that although a lot of math, but it's just the same as the spin qubit, almost exactly the same, right? So that's why we spend so much time in spin qubit. So now you can easily understand the rest. But how about two qubit gates? We also cannot go too deep because 2 qubit gates is under active research. It's difficult, right? I don't understand everything. But here I again show you one of the possible implementation. I will also take things for granted. We just assume it works for some of the statements, right? But you will see that you will try to borrow a space outside of your qubit space to do the 2 qubit gate, like what happened to the spin qubit. We discussed earlier. Okay, so let's see how we do it. The idea is this. Let's think about how to implement the C0 gate, right? But before implementing it, we will implement the control Z gate. Why control Z gate is good enough?
We can build it in qubit.
Yeah, we can build a control NOT gate by using single qubit gates, right? Single qubit gates is easy. And we showed that earlier already what the equation is. So we'll look at the control Z gate first. So first, again, understand what the physical system we have. It's trap ion. So what is trap ions? You build the potential well. Then you have an array of ion. Remember the Paul trap, the linear Paul trap? And due to Coulomb repulsion, they will just form like what you guys said, a lattice last time, right? It's a lattice. So if it's a lattice, it has vibrational mode, just like a crystal. Okay? So it has vibrational mode. Right? Which let me call it A. And because the temperature is very low, right? We cool it down using laser cooling to almost like to less than 1 millikelvin. So we can assume that we are only interested in 0 or 1. Here 0 and 1 means right 0 vibration or 0 photon. Let's say 0 photon, 0 number of photon. Okay, because photon is the vibration of the lattice, the collective action. Yeah.
So I had this question because I watched the video and was a little confused about the temperature. So you're using the Doppler
Cooling.
to cool it. So basically the cavity in which these ions are, they're not at millikelvin, right?
Right, correct.
You
So
don't need like a per se.
you're right.
But now the detector, in order to be low noise, has to be at somewhat cryogenic temperature.
You're saying what at
The
low? The detector. Detector need to be at low, yes.
Okay.
For two reasons. One is if you use this, no, we did not talk about detector, right? It's for the photonic qubit I'm going to talk about today. Yes, but your so-called detector is actually how you measure the qubit, right?
Yes.
To measure the qubit, what we do is actually just shine a laser pulse. And then if it's at 1 state, it will be excited. If it's 0 state, there's no enough energy for it to excite. And then so if it's 1, you are excited, then it will decay eventually, then you emit a photon. And then we decay the photon. If we see there's a photon emission, we know this is at 1 state.
Yeah, but the question is because the photon count is low, if your detector is not low noise, then you would miss, and that's generally why they make the detector operate at cryogenic temperature. That was
Yeah.
my understanding.
You can, that actually I'm not sure, but yes, if you go to 4 Kelvin is good enough, right, for this detection. You don't need to go to millikelvin. And in millikelvin, your photo detector might not work. But I think 4 Kelvin is good. But I don't know exactly what they use. But you're right, you want to reduce the dark current, right? The dark current noise.
Okay.
Right, yeah.
And is it also true that this capture rate is very slow because you're catching very few photons per the time pretty wide? So you have an advantage of high T1, T2, but the other disadvantage is your readout time is very long. So the net
Decay rate, it might be long.
decay.
Yeah, not capture rate, right? But so what I'm giving you is a very simple picture. The people also utilize other level to let it decay, which I don't know the detail. Yeah, so there's a lot of engineering there, right? So what I've been giving you is just 2s half and 2p half states. Is that correct? You remember what I gave you? Yeah, 2s half and 2p half states, right? But actually, if you read the paper I quoted, they also have other state which is not avoidable. You cannot inevitable. There will be state in between. But people also use those states to help some of the engineering, like the D state. Okay, so what I'm giving you is just a concept, how you do the measurement, how you do the detection. Okay, but the real operation, right, is more complicated than this. Okay. So let's come back to here, right, the 2 qubit gates. Again, I have this trapped ion. This is the array of trapped ion. And because they are array, they will have vibration, like collective action. But when it is so cool, so almost no vibration, or maybe one photon, one excitation. Okay? So you may have 1 photon or 0 photon. So this state is not referring to our qubit states. Remember, we have a qubit state in trapped ion, right? Just recall. We also have the qubit state, which we used to call it 0 and 1, but here I will call it the ground state and excited state. Okay? It refers to these two states. 2s half, f equal to 1, f equal to 0. Is it okay? So we have this hyperfine structure, right? If this hyperfine structure is bothering you, it's okay at this stage. Just forget about it. Just agree that due to the physics, we do have 2 qubit states. The separation is in the order of gigahertz or less. Yeah.
What does F stand for? Frequency?
No, it's the hyperfine structure quantum number.
Oh, just
Yeah, the hyperfine structure. Yeah. So, and both of these belong to S half. Okay, yeah.
So whereas in spin qubits, we applied a magnetic field to do this Zeeman spin. Here, you don't have to apply a magnetic field, but just the nucleus neutron itself acts like a magnet splitting the energy level.
Right. This is the interaction between the neutron quadrupole and the magnetic field generated by the electron. Okay. So there's an interaction between the nucleus, the nucleus and the interaction of the electrons. Okay. Then you have this splitting. Okay. Now, so just be clear, right? I don't want you to get confused. So now we are talking about ground state and excited state, and this 0 and 1 are talking about the photon. So there are two systems, right? We can form the tensor product. So the states can be possible states. I can say this is what? G0, my qubit is ground state, low photon excitation. G1, qubit is ground state, 1 photon excitation, means my qubit, the qubit I'm interested in, for example, qubit atom A. Atom A is at ground state. And then the whole train of the ion has 1 excitation of the photon. They are vibrating. It's the atom vibrating. Okay, nothing to do with the electron energy. Okay? Or it can be in excited state, no photon. Right? Or it can be at excited state, 1 photon. It is so cool, the system. So it is a it is good enough to account for this. Yeah.
So sorry, I want to make sure. The photon is part of the atom and not the lattice, or is it part of the lattice?
It's part of the lattice.
Okay.
So if you, like what you did in solid state physics, right? So we say you have a train of atom, let's say infinite, and then you say there can be vibration, and we can decompose all the vibration into a Fourier series component of different wavelength, right? So you have a minimum wavelength, which is just equal to maybe, I forgot, half of the atomic distance or double of the atomic distance. And then, or you can have very long wavelength, right? And then you can have dispersion curve, remember? If you have taken solid state physics before, you can have the dispersion curve, which related to the, this is related to the wave number, the wavelength, and then the energy, right? And you may have something like this. If you learned this before, if not, that is fine. Then we have this so-called acoustic photon, and then you have another mode, which is optical photon, something like that, right? It all just talking about what the possible mode of your vibration. This is not necessary here, but what we are trying to say is that, yeah, as a collective action of this ion, it's just like our lattice crystal, they have some vibration mode, which we'll call the photon.
So the atom adjacent to it also would have the same 0 or 1 state.
No.
But G or E would be
No,
different.
no, yeah. Okay, same 0 and 1 state. You are right, I'm sorry. So yeah, so I will answer your question later, right? So this is, let's say if only care about one qubit, and 1 qubit is the electron state in one atom, right? Then you have this, right? But if I care about 2 qubits, then what will happen? Then you will say, okay, I have Ga, Gb, 2 atoms, and then you still have 0 mole, and then you can have Ga, Gb, 1 photon, Ga, Eb, 0 photon, right? So in this case, etc. In this case, the B atom is excited. Okay? You have a question?
This other 0, 1 state.
Oh, maybe not exactly, because in this case, we are not trying to see how the qubit state is changing the vibrational mode. They are kind of fully decoupled into, yeah. So we are just trying to, I will show you later, we're trying to borrow the photon mode to do the computation, right? Because when you do computation, you're supposed to confine yourself in the 0, in the ground and excited state of the electronic state, right? But now we try to borrow this one so we can apply Control C operation. Yeah. So it's not like we are like in the resonator, we try to do the cross curve to change its resonant mode. Yeah, but this is a good linkage, try to link something. Yeah. Okay, so good. Your question actually helped me to clarify a lot of stuff. So now let's consider 2 atoms. Okay, because I want to do the 2 qubit gates, right? So I only need 2 atoms. Each atom has 1 qubit, right? Ion, sorry, yes. For neutral atom, they actually use the so-called Ripple state to do this control knot, but easier to understand than this one, actually, in my opinion. Yeah, but you're right, 2 ions, right? Now consider 2 ions, A and B, okay? Then what will happen? Then this is how we do the 2 qubit gate. So let's start with this. And this one you need to take it for granted. So we are going to step 1, okay? We will apply a pi pulse, okay, with so-called redshift energy. What does it mean by redshift? It means this energy, that is, the energy is smaller than the energy required to excite it from the ground state to the excited state. It's redshift. Okay? If it's not redshift, you know that if I apply a pi pulse, you are going to have Rabi oscillation, right? Bring it from 0 to 1, 1 to 0. Is that okay? Just give an example, right? This is just a fake example, really fake. For example, if I say this is omega 0, 1, okay? Then my energy may be For example, I can be wrong, but I hope that you don't take this for granted. Let's say I apply, this is the pi pulse, 900 megahertz, which is smaller than omega 1 equal to 1 gigahertz, for example. Just a fake example, can be wrong, okay? Do not take it too serious. But I'm just to show you that if I want to do the rapid oscillation, like what we did in previous case, right, without detuning. Redshift means we have detuning, right? In the last lecture, I do 1 qubit gate. I apply omega 1, which equal to the Larmor precession frequency, right? Omega 01, which is the Larmor precession frequency, right? Then apply the pi pulse, then it will just go from 0 to 1, 1 to 0. But now the energy, the photon energy, is less than the separation, right? So I cannot do any excitation. It makes sense? So think about this. If I have a state that is GA0, it means I at the ground state, atom A is at the ground state, right? I'm on the first floor, and there's no vibration of this building. Someone try to excite me, give me a laser pulse, but it is not enough to promote me to the second floor because I'm applying 900 megahertz energy instead of 1 gigahertz. Then what will happen? Nothing will happen. Yeah, because I cannot absorb the photon and then go to the second floor. But if I am actually at the excited state, okay, I'm on the second floor. But now it is quantum. In order to go to the first floor, I need you to give me 1 giga. Not you give me. It's that when I jump down to the first floor, I need to release 1 gigahertz of energy, right? From second floor to first floor, right? But this is resonant, right? Because you apply the pulse with me, right? Like stimulated emission or something, right? Then I have extra energy. This energy will go to create the vibration of this building, which is the photon. Okay? So I will go to the ground state, and it turned out to have a phase shift, right? So this one, I did not learn this, but I just take it for granted when we read the material, right? I probably just go through the math, that is the case. Negative I times the ground state, and one photon. What question you have?
So why would be exciting something?
Because you do have a laser coming to you. You do have a photon. You do absorb a photon also. You go from excited state to ground state, right? You release some energy, and at the same time, you also have that photon.
Yeah, but like, okay, it's releasing energy and you're trying to excite it.
Yeah, it just turns out this process will happen. And that's why this is difficult about 2 qubit gates. How do you know that this one will create a vibration? You just go through the math that will happen. Yeah, it's not straightforward, right? And the interaction can be weak. Yeah.
This is stimulated emission, right? That is the process.
Yeah, I think so. Because it does not go down without the laser pulse, right?
So you shoot a pulse.
No, but it's not actually. I don't know how to say. Maybe too difficult for me to say. They don't have this. It's not stimulated emission because they don't have the same frequency, right? Because my energy stimulated emission is like you give me the same energy, then we would shoot out another photon as the same energy, same phase as what comes in, right? But this is not. So this is a more complicated. How to say free bodies. I don't know how to say that. I'm not good at atomic physics, but just trust me. I don't understand this well, but you just not trust me. I trust others. The point is that you trust that, but it's okay for you, right? It looks everything makes sense. Does not contradict anything. It's just that the result is that I excite the vibration when I go from high energy to low energy, and this vibration. Besides that, I excite one vibration. I also change the phase by negative I.
My second question was going to be, how is that not low? It's negative.
Yeah, how does it? You probably it's just you go through the math, you will see that. But I never try to go through the math. Okay, I just show you one possibility. Yeah, so maybe you can dig into this by looking in the literature. Yeah. So similarly, right? If you are at the ground state and you have one photon, if you get this pulse, you will also get a phase shift to the excited state with no photon. Okay? So you see, this kind of makes sense. It's just a reverse process. Okay? But they all have negative I in front of it. This is the thing that probably most of you don't feel comfortable to accept. But unfortunately, I can only just say, let's trust this, right? Because I don't know also. I never try to derive. Now, maybe the idea of this class is like you know that something can be done and how it can be done. Exactly the math, then maybe when the time comes, then you try to dig into it. Okay? Okay, so the pi pulse, but we agree that, right, we need to have redshift because we don't want to touch it when it is at ground level. We only want to change it when it is in excited level. Why is that? Because it's related to the control gate. It means that I don't want to add a phase when you are at 0. I want to do something when you are at 1. This A is going to be the control qubit in the control knot and control phase shift gate. Is that okay? Okay, so let's continue. You will see more. Now then we go to step 2. What do we do now? In step 2, we are going to apply a 2 pi pulse. 2 pi pulse, you will just go from 0 to 1 and then back to 0, okay? And again, it has this one. What it does is that if, I forgot to say to the ion B, to the second qubit, okay, the target qubit, let's call it the target qubit. Okay, the first pulse was to change the control qubit so that I get the phase shift of negative I if it is at the excited state. The second pulse is to apply a 2 pi pulse so that this time is not redshifted. This is the exact energy, right? So if apply a 2 pi pulse, what will happen to this one? It will go back to its states, right? But you should remember when you go through the broad sphere, you actually gain a negative 1. You need to go through 4 pi instead of go back to your original position. So what you get is negative GB1. Okay? That's it. That's all I want to say, right? This is expected. This is the 2 pi pulse is nothing special. Okay? But then we need to bring the step 3. Right? But here I should give a note, right? Your ions are cool. Right? So you should start with A equal to 0. No phonon at the beginning. There should be no phonon because it's very cool, right? Then how can I get 1? Right? How can I get 1? So 1 must due to what? Ion A at EA, right? The whole system, I was cool to the 0 state, there should be no phonon. But now, why I would be able to have GB1 exist? It is only when I have 1 here, right? And this 1 must because I have the A was at E1, and then it create 1 for me.
Oh, A gave it to B.
No, A give to the phonon. Because A was in excited state, then you generate 1 phonon after the pulse 1, first pulse. If your A was at ground state, after the first pulse, you still did not generate any phonon. It is still 0. It's only when you were excited, then you will generate 1 phonon after the first pulse.
For A.
For A. No. For the whole train. Phonon is for the whole train.
Oh, okay.
Yeah.
All qubits.
Yeah, the whole system. Make sense? So you must build it. So here, just to tell you that, you see that then, how can I apply this phase shift? It's because my A was excited state, means the control qubit was 1. If my control qubit was 0, after step 1 and step 2, I cannot have this phase shift. Okay, again, GB0 is not going to give you negative, just because of the physics, which I have never verified. Okay. So step 3, all we want to do is just repeat step 1. Which means I'm going to apply a pi pulse. Again, it is redshift. Redshifted pi pulse means smaller energy than omega 01 to ion A. Okay, so what will happen? Now, all it does is, if you look at this pi pulse, all it does is that if you're at the ground state, then you will go back to the excited state with -1. Okay? So remember this rule, right? Then let's take a look how it works. I will just keep doing this. We just go through all the cases. I have A atom, ion A, ion B, and phonon number. These are the quantum number, okay? I can start with G0. Okay, yeah. Vibration mode, yes. The quantized vibration is called phonon. Yeah, it's a quasi-particle, not a real particle, but you treat it as a particle in your quantum mechanics. So what are the possible states of A and B? GG, GE, EG, and EE. Is this okay? At the beginning. And the phonon must be 0 because it's cool, right? We cool to very low temperature. Less than 1 milli Kelvin. So probably it's smaller than the excitation energy of the phonon. Or we say smaller than the energy you need to create 1 phonon. Okay, cool, right? So only 0. Okay, so everything looks okay. Then that's what I'm going to do. I'm going to apply a redshift pi pulse, a redshift 1. Okay, what will happen? So based on what we learned earlier, when you are at ground state, when atom A is at ground state, you have 0 phonon, no change. But if your atom A is at excited state, you have 0 phonon, it becomes ground state and 1 phonon with a phase shift of -I. Okay, so let's look at this. So what is the first case? The first case, yes. Because it's ground state, atom A is ground state, no phonon, so this is still G0. How about the second one? Second one, again, remember this one, when I apply the pi pulse, I apply the pi pulse to only atom ion A. Still the same, very good. Right, because it's still G0, right? So GE0. How about the third one? It is on excited state and then go to the, apply the pi pulse. If you forgot, take a look. Excited state for A and 0, it becomes negative I. Ground state for A and 1, right? So in this case, I get negative I. This becomes the ground state, and 1. Okay? And then the next one, what will happen? Negative I, G, E, 1. Very good, right? Second qubit, the target qubit is not changed, right? We only changed the first qubit just because we applied that, right? Okay, so this is the first pulse. Now let's go to the second pulse. Now apply a 2 pi to ion B. Okay, so again, just trust it. It only has effect if you apply the ground state with 1 photon. Okay, then you add a negative sign. So what happened to the first one? GB is at ground state, but no photon. Yes, so same. GG0. How about the second one? Also same because there's no photon. Okay, so this is GE0. How about the third one? I think I said something wrong earlier. No, I'm right. Is what? G1, you said negative, right? Because this is G1. G1 becomes negative G1, right? So it becomes IGG1. Because negative 1 times negative I. How about the last one? The same, because it's excited state with 1 photon. So nothing changed, right? So it's negative IGE1. Okay? So you already see that in this whole process, when the excited state, the control qubit is 1E, right? And then it only has some special effect, like negative I, if the second qubit is also in the excited state. Okay? Of course, you still have I here, but doesn't matter because the next thing we will do is another pi to ion A. Okay? So another pi to ion A, again, then let's check the table. It's not going to change anything except that you will either have excited state with 0 photon or ground state with 1 photon. And then they all apply the negative I and flip the state. So this is, anything happen to the first one? No, because it is ground state and no photon, right? So it is just GG0, nothing changed. How about the second qubit? Second set. Same, because again, the ion A is at ground state, right? So, and no photon, nothing changed. And how about the third one, GG1? Let's take a look again. GG1, G1, when first qubit as a ground, and then you have 1 photon, you apply a negative I, and it becomes the excited state, right? So negative I times I equals to what? Yeah, I times negative I. Right? I times negative I. And then it becomes EG0. Yeah? And this is 1. Okay? And then the last one, you have G and 1 go through the same process, right? But you have negative I times negative I, E0, which is equals to negative EE0. Okay? Now let me highlight the qubit. We don't care about the photon. Now photon is useless for us. GG becomes GG. GE becomes GE. EG is still EG, but EE becomes negative EE. And that is a control C gate. Okay? So we have implemented the control C gate, right? We did not know the physics. Unfortunately, I don't know neither. I did not go through the math. But we clearly see that, how does it work? It uses the vibrational mode, which is outside of the Hilbert space of the computation, to help it to do this interaction. This happens very often. In the neutral atoms, it's the same. You have two computational bases also at the bottom at these terms with this hyperfine splitting. That's good. But when you want to do interaction, you excite the atom to really high quantum number, n equal to 50, for example. You have a very large atom, right? Go to n equal to 50, not 1, 2, 3, 4, right? The largest we know maybe 7 or what for the largest atom. Go to 50. It's like micron size. And this guy is going to interact with, this is called Ripple atom, interact with another atom. And then whether you can excite or not, it depends on another atom state. And then you can create so-called Coulomb blockade. So when the other atom was at 1, then I cannot excite. And in order to excite, it also depends on the laser energy, because from 0 to this Ripple state or from 1 to this Ripple state need different laser energy, right? So if it is at 0, maybe I cannot excite it, then I don't feel the Coulomb blockade. Then I can excite mine. I don't feel the Coulomb blockade from the neighboring atom. I can excite mine. And so as a result, my phase shift really depends on its original state in that atom. Okay? Yeah.
So how do detectors?
No, you cannot measure phase unless you do you do interference. This is just implementing the gate, not the, right? Yeah. So we have implemented CC gate, and I hope you can recall this one, right? So this one, that's not my intention. This one is just equals to, this one is just equals to 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 negative 1, which is the control C gate. And we know that the control NOT gate, as we discussed earlier in the spin qubit case, right, is equal to I tensor product H times control Z gate times I tensor product H, which are just two separate one qubit gates. Okay, so we've implemented the control NOT gate. So that's all we want to discuss about the trap ions qubit. Is there any questions? Yeah.
You know, if I'm guessing like the phonon is like the energy in the phonon is probably related to like
the length of the train.
Yeah, the length and like the strength of the trap.
Yes.
They like tune that so that you get this interaction between photons and vibrational states.
I think so, although I don't know. Yeah. So again, right, because the vibrational mode really depends on how long your atoms are, and also the trap energy that you bring, how close they are. If you remember, if you have done solid state physics before, there is a constant, Hooke's constant, right? Effective constant, how they interact with each other. That is the one to help you to get the eigen frequency of the train, right? So yes, that it should depend on the type of atom interaction or even the well potential. Okay, good. So we are done with this. Let's go to photonic qubit. Yeah. Yeah.
Okay. So because I've seen them like kind of suspended
Oh,
in the string, but if
2D.
you wanted, you have to kind of do this thing in an array after an array, and I'm not sure.
Maybe I'm wrong. I was thinking about neutral atom.
Yeah,
I don't know.
yes.
I don't know. Yeah. I don't know